So next talk, we move to Hobart. We will listen from Petra Heil from Australian Antarctic Division. She will talk about marginal ice zone scoping, floe-scale sea ice property, and exploring wave ice processes. Petra, when you're ready, feel free to share your screen. Yep.
Yes, thanks, Pat. Thanks, everyone. Can you hear me?
Yep, please go ahead, Petra.
Yes, sorry, I'm just having trouble to share, unfortunately. Can you see the presentation?
Not yet, but yeah, please try again.
Oops. It says that I'm sharing.
Not yet.
Okay, sorry, I'm trying again.
Oh. Yeah, I think we can see your Linux desktop now. So yeah.
Can you see the presentation?
Yep, but not in full screen mode yet. You can change to full screen mode. Okay, thank you. Over to you, Petra.
Yeah, thanks. Oops. All right. Thanks, everyone. Really jealous that I can't be there. I tried to listen to some talks and sounds like a really great meeting. And my apologies for giving a bit an Andy Pole to Ian's beautiful talk just then, and also being a bit scatterbrained. There's a lot of going on at the Australian Antarctic Division in the operations space at a moment where I'm having to interact a lot. So for this presentation, I try to pull together two preparatory investigations that we have been carrying out in anticipation of the marginal ice zone study. Some of you might know we have had an approved project to go in a marginal ice zone on the icebreaker Nuinya August next year. The timeline has slipped, and so now we are kind of trying to recover something out of the operational schedule that becomes more and more compacted and compressed as the days in this week evolve. Regardless, we have done quite a bit of work, and I think in itself that's already exciting, and I hope I can share some of that with you today. I also need to acknowledge my really dynamic co-workers on that, and nothing would have been possible without them. So it's two sections, but we have Mukung, Heather, Yang, Sean, and Shuki working on a project that looks at different satellite data streams, and we investigate the correlations of the physical properties at the different seasons and trying to come up with kind of semi-predictive model about the changes into the ice zone areas, speaking the pack ice, the consolidated pack ice, and the marginal ice zone. In the second part, I mostly try to distract you with some photos of some recent work in the field and try to link it back to some theoretical work, and then how we map those data into models around the ice breakup, wave ice induced breakup. And that work is very much done together with Joey Furmans and a former student at the University of Melbourne. I guess the motivation for this work was also to understand the recent changes in the dips in the sea ice extent, especially, and I just realized I have labeled the years wrong, the extreme minimum of the Antarctic summer sea ice, which would have been in February 22, not 21. I can't remember, and sorry, I couldn't attend all the talks here in this week. If people talked a lot about the ICESat-2, it's a laser altimeter carried on a satellite, and it provides us, whenever there's cloud-free opportunities, freeboard observations of the sea ice cum snow entity floating on the ocean. So our interest is obviously on the Antarctic Southern Ocean sea ice. And here we just plot for 1 year the different, for different months per season, the returns of the ATL10, which is the processed freeboard thickness information. And so you see we get quite a decent amount of information back. And we are quite pleased actually to have the summer coverage, which is here indicated as the February one. But we were also, especially with few of the marginal ice zone, interested how much information we would actually still retain during winter and early spring in that marginal ice zone area. And you can see there are some gaps which are caused by obviously quite some cloudiness in that area. However, we are confident that there's quite a good amount of data coming back also during the time of an experiment. Also, what you already can see is obviously, if you follow the color scale, there's quite thick ice that's retained here on the western side of the Weddell Sea, and then there's obviously other known areas where we are having recurrent areas of very thick ice in the Bellingshausen and Amundsen. Thank you. So I don't know if you can see this funny thing, but I can't get rid of it. Apologies. So after we looked at the IZ2 freeboard information, we try to understand and gather a bit more knowledge and verify it. And so we basically went into the verification mode, and we looked where we found some quite thick ice in different parts of the Weddell Sea. So this is a zoom in of the Weddell Sea, and I will soon explain what the south and the west mean. And we verified it with ice age data, which Christian Melsheimer from the University of Melbourne provided to us. And so basically for the two regions displayed here, the west box and the south box, we just plotted for those years where we have coincident IZ2 data, the changes in the ice age. And you can see that there's quite a bit of multi-year ice kicking around at all time, especially in the western part, much less so obviously in the southern part, where we have these sea ice modifications, not least also because of the ice shelf processes. And what you can see basically is the seasonal cycle following quite well in both areas, but obviously much more pronounced in the western area, where the ice flows around with the gyre and sits over a much shallower topography and is very much affected by the compression and the strains that it experiences as it moves clockwise around the Weddell Sea. What you also can see is that there's a good amount of very new ice in that area, despite being basically within the Weddell Shire. And sorry, I can't see anyone. It's a bit the Zoom experience. If there are any questions or if you have problems hearing me, please let me know. A third remotely sensed data stream that we were looking at and very much rely on is the ESA Sentinel-2 imagery. And this plot just gives a snapshot of overlapping data. So that is for one winter season, we have plotted in dots the IZ2 tracks. The color scale actually indicates the ATL10 information. And then you see here underlaid the Sentinel-2, that's an optical sensor with chosen information. And so basically a lot of the figures that I show in the following will really refer to the boxes that I showed before. And this here is the motivation why we chose those boxes, because we had a lot of coincident tracks and Sentinel-2 data here along the western part of the Weddell Sea and some more across here in the southern part. We were really lacking this area, which is actually what we hope to explore with you on looking into marginal ice zone processes. So here's an example for a very one-to-one comparison between the IZ2 and the Sentinel-2 data. You see the Sentinel-2 image scale shown here. It's a situation where the ice state was quite loose, divergent conditions. We had a low pressure system going through not too much earlier. It's February, so the flows are moving basically in free drift. And here the red line shows you the particular IZ2 track that we are using. And here we show you the one-to-one comparison of the different, one-to-one comparison of the different tracks. So IZ2 has 6 laser beams. There are 3 strong and 3 weak beams, and basically we carry out the comparison for each of those beams and compare to what we get from the Sentinel-2 data. And what's shown here is the flow size derived from the IZ2 in the orange boxes, and the Sentinel-2 derived on image processing flow size distribution. And what you can see quite neatly is that there's quite a lot of very small flows in the image. The general trend across all the beams is that the blue Sentinel-2 data underestimates the larger flows, which here show up as the orange peaks in the IZ2, but on the lower end they are agreeing quite well. Perhaps a bit of bias of the Sentinel-2 to assume there's more smaller flows. We have done basically all the images. You saw two slides in the past, all the coincident occurrences. Here is a second example, this time for compacted ice. It's at the beginning of the spring season, and again you see the scale, and in red on the left you see the IZ2 track going over the Sentinel-2 image taken within a few hours of each other. And again on the right-hand side, you see the comparison for all the 6 individual IZ2 beams, which are not resolved at a scale here. So basically all 6 look down at this very narrow red strip on the left image. What we see here is that the IZ2 very much has lower numbers, identification of the small flows. And that's a correction that we need to allow and consider when we use the more prolific Sentinel-2 data, basically to fill in gaps between the IZ2 data. That Sentinel-2 very much overestimates during the time of compact ice conditions, the flow sizes. So basically, backing up what we have done and also explaining it with the flow chords, which is one of the shared NSIDC shared parameters from IZ2. We feel quite confident that our information is correct and that we actually can use the Sentinel-2 data to approximate flow size distributions where there is insufficient IZ2 data. Remember, Sentinel-2 is a 2D image taken wherever we have cloud-free information. It spans much of the Southern Ocean, of the ice-covered Southern Ocean, while the IZ2 is a long track, and we have quite a slow repeat coverage. I think 30 days for near repeat and 90 days for complete repeat. So those 2 figures on the bottom convince ourselves that we are okay to use Sentinel-2 to fill in gaps within the IZ2 data. And so basically carrying out this investigation now for all 3 years of the IZ data, 2019 to 21, and separating it into a western box, the bottom plot, and the southern box, which is the other 3 boxes, we come up with the seasonal distribution of the flow chord distribution from the joint sensors. And there's probably scientifically not much surprises in there. We see that especially the blue one is the summer, December, January, February season. We see that we have a very large amount of small flows during that time, and a much lower amount of at the bigger end of flows, which is what we expect. We have open water adjacent to much of the ice in those boxes because as you can see here, during summer, the pack ice retreats and basically leaves much of the Weddell Gyre ice free. We also want to point out that there is quite a bit of an interannual change. And for example, in the first year, we find that the seasons at a higher end don't show much difference. So nearly during all seasons, we have kind of low coverage at the bigger end of the flows. That is here 10 kilometer scale at this end of the figure, while in the year 2020, we actually have observed, especially during winter and autumn, southern autumn, quite some higher numbers. So the currents went up fourfold during that year compared to 2019 and 2020. So to summarize this first part, sorry, just trying to find the time. We have demonstrated that there's quite a large seasonality in the ice age information that we were provided by Christian Melzheimer, and we know that this is influencing the properties of the sea ice, especially in the south and in the west of the Weddell Sea, and the exploration of why they are so different. I guess I don't need to explain to this audience, especially not following Ian's presentation. There is quite a wealth of satellite imagery. However, the altimetry data are very sparse, so we have to look into the other data. And so for us, the Sentinel-2 image, I've forgotten this means IS2 data are sparse. So we have to look into the Sentinel-2 data to basically backfill a lot of the area where there are no information from ISAT. Apologies, this year's ISAT-2 is sparse, Sentinel-2 we have a lot more coverage. We have focused on flow chord, flow size for this presentation. There is a clear seasonality, and we also can attribute the regional processes to different conditions and to degree in the atmosphere, but also very much from what's driven in the ice regime. So we have the much more open and free conditions in the southern box and the more compacted and topography-driven processes in the western box. And now for something completely different. Another study and preparation for this infamous MIZ study is to get ready and develop actually a whole heap of sensors that allow us from the vessel, but also autonomously from expendable instrumentation to understand and measure the sea ice, the ocean and the atmosphere above, and also then to derive information, for example, how wave and ice interact and how the ice zone evolution can be traced back to changes in the marginal ice zone. So we have seen over the last decades various people successfully measuring and observing the ice breakup. However, for us was the challenge to identify some effective and affordable instrumentation. And so we have over the last 3 years worked mainly on the fast ice of KC Station, which is in East Antarctica, south of Perth in Australia. We have been using the KC fast ice basically as a accessible sea ice base to really get on top of our design and refining the instrument development. During the last 3 years, 2021 and 22, the last weeks, we have developed different kinds of buoys and have deployed them. So those dots here show you what we had out or still have out in this September, October. And this year we were able to test all 3 buoys that over that experiment have been developed. They are the wave ice buoys in green, which we put further out because we expected to lose them, and we are quite confident that our buoys are developed enough to measure the ice breakup and changes, especially with few of deployments out in the marginal ice zone. We have gone back to the geophone that we had some tests last year, but refined it, and we have had quite some good data collection this year. And we also put in 3 more hydrophone buoys. They are much more expensive, especially with the need to relay a larger amount of data. that can't be filtered or downsampled on the buoy itself. And so we were quite careful deploying them, and we actually have recovered them from the KC fast ice to work with them again. This is just how simple the buoys look, basically by a pelican case, put some smart stuff in it, and put a transmission antenna on the outside, and off you are. Obviously, the hydrophone buoy has an umbilical cord with a hydrophone that needs to be submersed below the sea ice into the surface ocean water. And the geophone has a sensor that will be inserted in the ice and measures the vibrations. And I should acknowledge that this work couldn't be done not only with the smart people and postdocs working on that, but very importantly, the dedicated effort by quite some field officers, field training officers, which the Australian Antarctic Division uses to go out in the field. And they're really quite happy to do this work, but obviously if we go them to dig around the snow and ask them, why is our buoy at the moment not transmitting, and they had a big snow dump, they were not quite as happy. So this picture was taken at the end of September, and we tried to understand why some buoys actually didn't send us any remote data. And they said, yeah, it was on a good half meter of snow. So it's hopefully something that we don't have to worry about in a marginal ice zone. Using the geophone information and just showing you here some of the data that came back from the fast ice last year. G1 deployed or measuring deployed in the end of August, but here measurements from September. You see that sensors are quite capable to pick up a number of cracking events, and we verify them through a number of satellite data, but also through visual observations from the crew at KC, to where they could see new cracks in the otherwise undisturbed fast ice. And Joey has been working on basically extracting thresholds to derive the modulus about that's required to actually say this is a breakup or an event that would be sufficient enough if there was the right kind of wind motion to actually dislodge the fast ice and carry it away, similar to a ice flow breakup event. Working on the fast ice, you have to benefit basically if the fast ice doesn't go, you're measuring a whole heap of other events that are further towards the coast. And this year we had actually for the first time our buoys released, the G1s, the ice wave buoys. And you can see here just on the MODIS imagery, we deployed them, the field training officers deployed them at the end of August. Not much happened. We were worried a bit about the buoys running out of batteries and all that before any action happens. Usually the ice in that area is expected to break out in September. So here again, you see Casey. We play in the Swain area, which is like 15-20 kilometers to the north. So we are not impacted by any icebergs in the area down here or islands. And finally, 2 months after deployment, the outermost two buoys actually were moving out. And we just here tracking and trying to understand on the MODIS imagery what the buoys do and how to interpret the signals. Unfortunately, compared to the last 2 years, it was very cloudy and we didn't get many coincident MODIS images. So
Yep,
this here shows
sorry,
you...
Petra, for interruption. Maybe you have to wrap up maybe about 1 minute. Yeah.
Yes, no worries. Here is the MODIS imagery, the buoy track. Then it's basically verifying with the MODIS imagery, explaining the drift speed as it passes through Paulinia. And also here, just going back to the breakup. And in real talking into the black ether, sorry, I love Zoom, but it's really hard to know the timing. Here's just how all this data will basically be processed. We take the wave measurements, we derive the acceleration, and then with some of the equations that I think others presented on Wednesday also, we derive the breakup parameter. And then finally, we are able to basically insert a modulus into coupled models like Josh has done here. Josh was a student with us, and he had a coupled size wavewatch 3 model, and he basically run different simulations based on the buoy observations, the measurements we had, and basically run his own buoy as tracers in the model, and that looks quite promising. So that's it from me. Thank you.
Yep. Thanks again, Petra. Yep. Maybe because just we have morning tea after this, maybe we have time just for one very quick question. If you have some here online. Oh yeah, just one quick question. Oh yep, please.
Hey Petra, it's Luke here.
Hi.
Where did the value of the Young's modulus come from? Did you measure the material properties of the fast ice?
Yes, so at the visitations we get ice cores extracted and take some measurements in the field and in the lab, and then we actually do a full analysis of the ice cores back here. Yeah.
So it is measured.
Yes.
It's not tuned. Okay.
Sorry, another comment from Mike. Yeah.
Yeah, I had the same question, Petra, because we use a different value. We use 6 by 10 to the 9. You use 3. So I'm just, is it an in situ measurement that you made from the? Did you determine it from the crack speed or something like that, or was it measured in the lab?
No, that is actually from the ice samples coming back and going into the lab.
Okay. Yep. Thank you.
Yeah.
Yep. Thanks again, Petra, for your talk, and yeah, everyone.